you walk into a modern building, right? Or maybe you've seen those robot arms in a factory video. Ever stop and think how all that complex machinery, I mean, from just one little valve to a whole skyscraper's climate system, how it's all coordinated? Well, often it's down to this unseen but incredibly powerful type of computer. Today, we're doing a deep dive into programmable logic controllers, PLCs. You hear them called the real workhorses of industrial automation. And we'll also look at their sophisticated cousins, building automation systems, or BAS, that manage entire intelligent buildings.
Yeah, our mission today is really to pull back the curtain on these brains behind automation.
Hmm.
We'll dig into what they actually are, how they're built so tough, how they connect that digital logic to the physical world, circuits, devices, and the different ways you actually program them. And then we'll scale that up, see how those same ideas manage whole smart buildings.
Think of this as your shortcut, really, to understanding these complex systems, the ones that underpin, well, pretty much all modern infrastructure and industry. Hopefully, you'll have some serious aha moments about the tech running your world. Okay, so let's unpack this a bit. What exactly is a programmable logic controller? Why are they so crucial in industry?
Right, so at its heart, a PLC is a specialized computer. It's built specifically for controlling industrial processes and machines. Think manufacturing lines, oil and gas operations, even water treatment plants. But what's really fascinating is why they became so dominant. They basically replaced these older, incredibly complex relay logic control systems. I mean, imagine just miles and miles of wires for every single decision point.
Wow, yeah. Hard to even picture now.
Exactly. PLCs brought flexibility, but also ruggedness. They're designed for harsh industrial environments, dust, vibration, electrical noise, places where your average desktop PC wouldn't last a day.
So it's not just about handling complexity, it's that sheer reliability factor, too.
Absolutely key.
What are the core functions then? What does a PLC do that those old relay panels just, well, couldn't?
Well, beyond just the complex logic, PLCs are constantly monitoring inputs, signals from sensors and switches. They process that information based on the program, and then they control outputs, sending signals to actuators, motors, valves, lights, you name it. But it's more than that. They also handle data storage, communicate with other systems like HMIs or networks, manage precise timing, and crucially, perform fault detection and diagnostics.
That fault detection sounds like a massive step up. Just knowing immediately if something's wrong.
Huge. It means they're not just blindly executing commands. They're actively monitoring the process and their own health.
So, besides fault finding, what were the key features that really made PLCs the standard over those old hardwired relays?
I'd say three main things really stand out: programmability, expandability, and maybe surprisingly, reduced overall cost in the long run.
Okay, let's touch on this. Programmability seems obvious, but what does that really mean in practice?
It means you can implement really complex control strategies relatively easily. And importantly, you can change the program, often while the system is running, which drastically cuts downtime compared to rewiring relays. Plus, graphical languages like ladder logic mean electricians, people familiar with schematics, could learn to program them without needing a computer science degree.
That's a big accessibility point
Yeah.
and expandability.
Crucial for growing systems.
Hmm.
You can add more input or output points by just plugging in extra modules or link multiple PLCs together over networks like Ethernet. The system can scale with the need.
And reliability. You mentioned ruggedness.
Yes, they use solid-state electronics, no moving parts like relays. So they last longer, switch faster, and they're designed with protection against electrical spikes and noise common in industrial settings.
Okay, and the last point, reduced cost. I mean, a PLC itself isn't cheap.
True, the initial component cost is significant. But for large, complex systems, think about the cost of designing, building, wiring, housing, and maintaining a massive relay panel. It's enormous. With a PLC, most of that control complexity moves into the software. Less hardware, less space, faster build time, and troubleshooting. Way easier, because the PLC program itself can often help you pinpoint the fault.
Right. It really makes you appreciate the unseen engineering. You just see an automated production line, maybe, but behind it are these robust, specialized computers making constant split-second decisions. Okay, let's get under the hood a bit. Let's look at the actual hardware. What are the main components inside a typical modular PLC?
Right, so typically you're looking at four major pieces. There's the processor, which is the CPU, the brain. Then you have the input-output modules, the I/O. There's the backplane, which connects things. And finally, the power supply.
The processor, the CPU, that's doing all the thinking, right? It's got the actual CPU chip, memory, communication ports.
Exactly. And a key spec here, something our sources mentioned, is scan time. That's how fast the processor can run through its entire program logic.
And that's critical, I assume.
Absolutely critical,
Uh,
especially for processes needing really fast responses, maybe rapid adjustments or emergency shutdowns. Milliseconds matter in those situations. And memory isn't just one thing in a PLC. It's usually a mix. You've got fast RAM for ongoing calculations, but it's often volatile, loses data on power loss. So crucially, you also have non-volatile memory, like flash or EEPROM. That holds the actual program and critical data, ensuring it survives power cycles. That reliability is paramount. Some systems even use non-volatile RAM for critical operational data.
okay, brain and memory sorted. How does the PLC actually, sense the real world and then make things happen? That's the I/O modules, isn't it?
Precisely. The I/O modules are the PLC's connection to the outside world. Its senses in its hands, if you like. Input modules take information from field devices like, is this button pushed? What's the liquid temperature? Is this motor overloaded? And output modules send commands out to field devices, turn this light on, open that valve, start this motor.
And I gather there are different types of I/O, discrete versus analog.
That's right. Two main categories. Let's start with discrete I/O. This is the simple on-off world, binary,
Yeah.
1 or 0. Discrete input, or DI cards, just read a voltage signal, usually 24 volts AC/DC or maybe 120 AC. Is voltage present a 1 or not a 0? They often use something called an optoisolator, basically a little LED and a light sensor, to create a physical electrical barrier. Protects the PLC's delicate insides from nasty stuff happening in the field wiring.
Smart. And discrete outputs.
Discrete output, the O cards, work similarly. The PLC program tells an output to turn on, and it closes an internal contact, usually a small relay or a solid-state switch. These are often dry contacts, meaning you need to supply external power through that contact to actually run the connected device, like a small indicator light or maybe the coil of a bigger relay.
Okay, so that's on-off. What about analog I/O? Sounds more sophisticated.
It is. Analog I/O deals with signals that can vary continuously over a range, not just on or off, but levels, measurements. Typically, you see standard ranges like 0 to 10 volts DC or 4 to 20 milliamps DC. Analog input, AI cards, read these varying signals from sensors or transmitters, giving the PLC precise measurements, things like temperature, pressure, flow rate, motor speed.
And analog outputs.
Analog output, AO cards send out those varying signals. So instead of just turning a motor on or off, you could send a 0-10V signal to a variable frequency drive, a VFD, to tell exactly how fast that motor should run. Much finer control.
Right, makes sense. Beyond the standard DI, DO, AI, AO, are there other types?
Oh yeah. You get special I/O modules for specific tasks. Things like high-speed counting, precise motion control, reading specialized temperature sensors like RTDs directly, and very importantly, safety relay modules. These are designed for critical safety functions, like emergency stop buttons or light curtains. They often operate somewhat independently of the main processor scan to ensure immediate safe shutdown in an emergency.
That sounds crucial for machine safety.
It is, and for large facilities, there's also remote I/O. Think of these like smaller I/O racks without their own processor. They sit out near the equipment, collect the inputs, and send the outputs. But they communicate back to the main PLC processor over a high-speed network, maybe fiber optic or coax cable. Saves a massive amount of wiring over long distances.
Clever. And all these modules, they need to talk to the processor and get power, right? That's the backplane.
Exactly. The backplane is essentially the circuit board, often at the back of the rack, that provides the communication bus and distributes power between the processor and all the I/O modules plugged into it. Some newer modular designs integrate this into side connectors, but the principle's the same.
And the power supply.
The power supply provides the clean DC power needed only for the PLC processor and its modules. It's deliberately separate from the power used for the field devices.
Why is that separation so important?
It's a critical safeguard. If there's a short circuit or a ground fault out in the field wiring connected to an input or output module, you don't want that fault taking down the PLC's brain. It isolates the sensitive control system.
Got it. And you mentioned modular PLCs. Are there other types?
Yeah, you also get what are often called brick or shoebox PLCs. These are all-in-one units, processor, power supply, and a fixed amount of I/O, all in one compact box.
Pros and cons.
Well, they're usually cheaper and simpler for smaller control tasks. But the big drawback is limited expandability. You get what you get. If you need more I/O later, you might be out of luck. Modular systems offer much more flexibility for growth.
Okay, so we have all this impressive hardware. How do we actually make it do anything? Programming.
Yep.
Yeah.
Almost always programmed using specialized software running on a standard PC. You write the logic, the software compiles it, verifies it, and then downloads it to the PLC's memory.
How does it connect? USB network.
Usually USB or Ethernet these days. Older systems might use serial COM ports, and modern systems, you can often program them remotely over wireless networks or even cellular connections.
Convenience, but maybe security concerns there.
Definitely a factor. Which brings up another point. Our sources mention that physical keyed switch some PLCs have.
Ah, yes, you mentioned that. What's its role again?
It's a physical security layer. You might need to turn the key to a specific position program or remote to allow a new program to be downloaded. Turn it to run, and downloading is blocked.
So it prevents accidental overwrites.
Exactly, or malicious ones. It's a simple but effective barrier against accidentally uploading a faulty program or even certain types of cyber attacks.
And once the PLC is programmed and running, how do people, operators on the factory floor interact with it?
That's where the human-machine interface, or HMI, comes in. These are the screens. Could be a basic text display, could be a sophisticated touchscreen panel. They let operators monitor what the process is doing, see temperatures, pressures, statuses. They can issue commands like starting or stopping a sequence, changing set points, and importantly, view alarms and diagnose faults. It's the window into the PLC's world.
Okay, let's try and make this really tangible now. We've got the PLC logic, we've got the I/O modules. How does that connect to the actual pumps, valves, sensors out in the field? Let's start with those discrete circuits, the basic on-off stuff.
Right. Discrete input circuits are pretty straightforward. You've got a field device like a push button. When you press it, it sends voltage, say 24 VDC, to a specific DI terminal on the PLC input card. The PLC sees that voltage and registers a 1 for that input point in its memory. Release the button, voltage disappears, PLC sees a 0 punt. The wiring is often simpler than old relay logic because all the complex decision-making happens inside the PLC program, not in the physical wiring between contacts.
And discrete outputs, powering something.
Similar idea, but in reverse. The PLC program decides to turn an output on. It closes an internal contact on the DO card. You'll have an external power supply wired through that contact and then out to the device you want to control, maybe a pilot light or the coil of a motor starter.
You mentioned interposing relays earlier. Where do they fit?
Often right here. The contacts inside a PLC DO card are usually quite small, rated for low current. If you need to switch a larger load, like a big motor starter coil that draws significant current, you don't want to run that directly through the PLC output. So the PLC output energizes the coil of a small interposing relay, and that relay's larger, more robust contacts handle switching the power to the bigger load. It protects the PLC output card.
Makes sense. Protect the sensitive brain. Now, analog circuits, they're a different beast entirely, right? Carrying more detailed info.
Yeah, totally different. Instead of just on or off, an analog circuit carries a signal that's constantly varying, representing a measurement or a control level, like temperature, pressure, speed. Each analog input or output typically needs its own dedicated two-wire circuit. And the signal, whether it's current like 420 mA or voltage like 010V, travels in a closed loop.
And the wiring itself needs special care.
It does. Because these are often low-level signals carrying precise information, they're susceptible to electrical noise or interference from other nearby cables, especially power cables or motor wiring. So, you almost always use shielded twisted pair, STP cable. The twisting helps cancel out induced noise, and the shield provides protection from external electrical fields.
And grounding that shield is important.
Critically important.
Yeah.
But you only connect the shield wire, the drain wire, to ground at one end of the cable run, usually at the control panel or PLC end.
Why only one end?
If you ground it at both ends, you can create what's called a ground loop. Differences in ground potential between the two ends can cause unwanted current to flow through the shield, and that current can actually induce noise onto your signal wires, corrupting the measurement. Single-point grounding avoids that.
Ah, clever. Now, for analog inputs, that 420 milliamp standard is really common. Why 4 mA is the 0 point, not 0 mA?
That's a brilliant bit of design, actually. It's called a live zero. If the signal drops below 4 mA, say, to 0 mA or 2 mA, it doesn't just mean the measured value is 0. It indicates a fault. The loopy's broken, maybe a wire came loose, maybe the transmitter failed.
So it's got built-in diagnostics.
Exactly. It allows the PLC system to distinguish between a true zero reading at 4 mA and a problem in the circuit below 4 mA. Provides inherent loop monitoring. 20 mA typically represents 100% of the measured range.
And the 0-10 volt standard?
Also common, but it lacks that live zero feature. 0 volts could mean a true 0% reading, or it could mean the wire's broken. So for critical variables where you need that fault detection, 420 mA is often preferred. But 010 is perfectly fine for many applications, and these analog signals are usually very accurate, often within plus or minus a quarter% of the full range. You can even do quick calculations to check if a transmitter is sending the right signal for a given measurement.
And analog outputs, sending signals out.
Yep, sending those 010 IV or 420 meg signals out to control devices. A classic example is sending a signal to a VFD to precisely set the motor speed. The PLC can adjust that output signal on every single scan cycle, allowing for very rapid dynamic control of the process.
That sounds like where things like PID control come in.
Exactly. Proportional integral derivative control loops often use analog outputs to make continuous, fine-tuned adjustments to maintain a process variable right at its set point. Very common in process industries.
Okay, so we know how the circuits work. What about the actual devices connected at the ends of those wires? Let's start with the discrete field devices, the on-off ones.
Sure. You've got your manual pilot devices, things humans interact with directly, start-stop push buttons, emergency stop buttons, the big red mushrooms, selector switches, maybe joysticks for manual control. Then you have automatic pilot devices. These react to process conditions automatically. Think float switches for liquid level, pressure switches, temperature switches, limit switches that detect physical position, proximity switches that detect objects without contact.
Now, our sources make an interesting point about using these automatic switches, like a pressure switch. They're good for safety, but maybe not primary control.
That's a really key distinction, yeah. An automatic switch is excellent as a failsafe. For example, on a compressor system designed to run between 100 and 200 psi, you might have a high pressure switch set at 220 psi. If something goes wrong and pressure exceeds that, the switch trips and tells the PLC to shut the compressor down. Essential safety backup.
But you wouldn't just run the compressor by turning it fully on at 100 psi and fully off at 200 psi using only that switch.
Generally, no. Not for efficient or long-term operation. Constantly starting and stopping a large motor like that causes huge electrical inrush currents and mechanical stress. It dramatically shortens the motor's life and wastes energy.
So how would you control the pressure normally?
For primary control, you typically use an analog pressure transmitter that gives the PLC a continuous 420 mA signal representing the exact pressure. And the PLC uses an analog output to control a VFD, smoothly adjusting the compressor motor's speed to maintain the pressure precisely within the desired range. Much more efficient, much gentler on the equipment. The switches are just there as the safety net.
Got it. Switches for backup, transmitters, and VFDs for the main job. What other discrete inputs might you see?
You often get status contacts feedback signals from other equipment. For example, a motor starter might have auxiliary contacts that tell the PLC if the starter is actually energized or if its overload relay is tripped. And pulse contacts, sometimes called polarizer contacts, these come from devices like flow meters. Instead of a continuous signal, they send out a brief electrical pulse for every unit of quantity that passes, say, 1 pulse per gallon. The PLC can then count these pulses to precisely track cumulative flow.
Okay. And on the output side, discrete PLC output devices. We mentioned interposing relays and signal devices.
Right. Interposing relays protect the PLC outputs when switching larger loads. Signal devices provide visual or audible feedback pilot lights showing status, alarms, horns, beacons, and discrete actuators. These are devices that perform a physical action based on an on-off command. Common examples are solenoid valves, electrically open-closed valves, flow dampers or louvers in air ducts that slam fully open or fully shut, or locking actuators. Even VFDs can have discrete inputs controlled by PLC outputs for basic functions like start, stop, or forward-reverse direction.
You mentioned safety torque off earlier, too. That's a discrete output function.
Yes, a critical one on modern VFDs. It's a dedicated safety input circuit on the drive. A discrete output from the PLC, often via a safety relay, needs to energize this STO input for the VFD to be able to power the motor. If that STO circuit is broken, maybe by an emergency stop button or a safety gate switch, the VFD immediately removes power from the motor windings, regardless of what the main PLC logic or speed command is telling it to do. The motor coasts to a stop. It prevents accidental restarts and is a cornerstone of modern machine safety.
Okay, really important safety layer. Now, switching gears to analog field devices, these are sending or receiving those varying signals for precise measurement and control.
Exactly. On the input side, you have sensors and transmitters. Sometimes a sensor, like an RTD, resistance temperature detector, can interface directly with a specialized PLC RTD input module. This can be cost-effective if you have many temperature points close together. More commonly, though, you use a transmitter. A transmitter takes the raw signal from a sensor, which might be very low level or nonlinear, and converts it into that standard, robust 420 mA or 010V analog signal.
Why use a transmitter?
That standard signal is much less susceptible to electrical noise and inaccuracies caused by the resistance of long wire runs. It conditions the signal for reliable transmission back to the PLC. And transmitters measure all sorts of things: temperature, pressure, flow, humidity, pH levels, gas concentrations, vibration, load or force, speed, position, fluid level, you name it.
And you mentioned loop-powered transmitters. That sounded interesting.
Yeah, they're quite clever. These are specifically for 420 mA signals. The transmitter actually draws its own operating power directly from the 4 mA minimum current flowing in the two-wire signal loop itself.
So no separate power wires needed for the transmitter.
Exactly. Just the two wires for the analog signal loop simplifies wiring significantly. Plus, they're inherently low-power devices, which often makes them suitable for use in intrinsically safe installations in hazardous locations where sparks are a major concern.
Very neat. And finally, analog PLC output devices. What receives these varying signals?
We talked about VFDs receiving analog signals to precisely control motor speed, frequency, or torque. That's a huge application. You also have analog actuators. Unlike discrete actuators that just go fully open or closed, these can position themselves anywhere in between based on the analog signal.
Gra-
Think modulating control valves that can be, say, 37% open to precisely regulate flow, or dampers and louves in HVAC systems that adjust airflow based on a 0-10 signal.
Fine-grained control.
Precisely. And one more interesting device for systems that mix electrical control with older pneumatic systems: the IP converter.
IP, electrical to pneumatic.
Yep. It takes a standard 420 mA electrical analog signal from the PLC and converts it into a proportional pneumatic air pressure signal, typically in the range of 3 to 15 psi. This allows a modern PLC to control older pneumatic valves or actuators, bridges the gap between technologies.
Okay, fascinating range of devices. So we've got the hardware, the connections, the field devices. Now, how do we actually tell the PLC what to do? How do we program its brain? The software's become more user-friendly, you said.
Definitely. The programming software has evolved a lot, and there are several standard languages people use, defined by the IEC 611313 standard. Our sources highlight 4 common ones.
And what are they?
The most common are probably ladder diagrams, often called LD or just ladder logic. Then there's function block diagrams, or FBD, sequential function charts, SFC, and structured text, ST.
Do they all work fundamentally differently?
They look different, and they excel at different things, but they all operate on the same core PLC concepts. They all use input elements tied to physical inputs, output elements driving physical outputs, or maybe controlling a VFD over Ethernet IP these days. They all make heavy use of internal memory bits, basically internal software flags or variables, from a single on-off bool bit up to complex 64-bit LReal floating point numbers. These are used purely inside the program logic to simplify control sequences, hold intermediate values, and reduce the need for external wiring or relays. And they all have built-in function blocks for common tasks, like timers, think time delay on, TON, time delay off, TOF, and counters, count up, CTU, count down, CTD, even high-speed counters for fast pulse inputs. These are fundamental building blocks for sequencing and tracking events.
Okay, let's break down those languages. Ladder diagrams first sounds like an electrical drawing.
It looks very much like one, which is why it became so popular, especially with electricians transitioning from relay logic. It's graphical. You have vertical power rails on the left and right. Horizontal rungs contain the logic. On the rungs, you place contacts, which represent input conditions, could be a physical input, an internal memory bit, or timer counter status. And you place coils, representing outputs, a physical output, an internal bit, or starting a timer counter.
And the logic.
It's essentially Boolean logic represented visually. Contacts wired in series on a rung are an AND condition. All must be true for power to flow through. Contacts wired in parallel are an OR condition. If any one is true, power flows. A contact shown as normally closed is a NOT condition. It's true when the underlying input bit is off. Power needs to flow through the logic on the run to energize the output coil on the right.
So very visual for basic logic and motor control, maybe.
Exactly. Very intuitive for things like start-stop circuits, seal-in logic, basic sequencing.
Okay, next up, function block diagrams, FBD.
Another graphical language. But instead of contacts and coils, you use predefined function blocks. Each block represents a specific operation, maybe a timer, a counter, a mathematical operation, or even a complex algorithm like PID control. You wire inputs and outputs between these blocks. FPD is often really good for complex analog signal scaling, advanced counter applications, or visually representing more complex data manipulation or control loops where ladder logic might become cluttered or cumbersome.
Okay. Then sequential function charts, SFC, the name suggests sequence.
Precisely. SFC is specifically designed for processes that happen in a distinct, ordered sequence. Think assembly lines, batch processing, machine state control. It uses graphical elements, steps where actions happen, transitions, which are the conditions that must be true to move from one step to the next, and actions, the tasks performed within a step.
So it enforces order.
Yes. The logic flows from step to transition to the next step. A step must complete its actions, and the following transition condition must become true before the sequence can advance. It's excellent for visualizing and managing the overall flow of a complex process. It can even handle parallel sequences branching off and rejoining. Great for high-level control, sometimes used to manage the execution of other programs written in ladder or FPD.
And the last one, structured text, ST. That sounds more like traditional computer programming.
It is. ST is a high-level text-based language, similar in syntax to Pascal or C. It uses standard programming constructs like if than LC statements, while do loops, case statements.
So less visual.
Much less visual than LD or FPD. It might seem less immediately readable if you're used to the graphical languages. However, ST really shines when you need to implement complex mathematical calculations, string manipulation, complex algorithms, or intricate decision-making logic. Trying to do really complex math in ladder logic can become incredibly messy and inefficient. In ST, you can often express the same complex logic much more concisely and clearly using just a few lines of code. It's often preferred when graphical methods become unwieldy.
So different tools for different jobs, essentially.
Exactly. Most modern PLC programming software supports multiple languages, sometimes even within the same project, so programmers can choose the best language for each specific task.
Okay, this has been a fantastic look at PLCs. Now let's take that real conceptual leap you mentioned earlier. What happens when you apply these same kinds of principles, monitoring, control, logic, but apply them to manage an entire building?
Then you enter the world of building automation systems, or BAS. You might also hear them called building management systems, BMS, or building control systems, BCS. Fundamentally, it's a computer-based system, quite similar in principle to a PLC network, but its purpose is to monitor and control a building's mechanical and electrical equipment.
Similar to PLCs, but different. How so?
Well, the core functions are similar, managing inputs and outputs, executing program logic, being customizable. But the key distinction lies in the intended application and the environment. A PLC, as we've discussed, is typically a very rugged industrial computer focused on controlling a specific, often complex manufacturing or process task. A BS controller usually lives in a much cleaner, less harsh environment, like an electrical room or office space, so it doesn't need quite the same level of industrial hardening.
And its focus is broader.
Much broader. A BAS is designed specifically to integrate many different, often disparate control systems throughout a building. Think HVAC, lighting, security, fire systems. It centralizes the monitoring and access to all these systems, but often employs a more decentralized decision-making structure out in the field. The goal is holistic building management, enhancing occupant comfort, improving safety and security, optimizing energy efficiency, and streamlining facility operations.
Okay, so what kinds of building systems does a BAS typically pull together and manage?
Oh, the list is pretty extensive and always growing as buildings get smarter. But the core ones are definitely heating, ventilation, and air conditioning HVAC. That's often the biggest part. Then you have lighting control, maybe based on occupancy sensors or time schedules, energy management monitoring, electrical panels, meters, power quality, security systems, access control card readers, surveillance cameras. Fire alarm and life safety systems are crucial. The BAS often monitors the fire alarm panel and can trigger coordinated responses, like shutting down HVAC fans to prevent smoke spread or unlocking certain doors. Also, elevators and escalators, plumbing and water management, like monitoring tank levels or detecting leaks, backup emergency generators, even things like parking management systems in large facilities.
Wow, it really is the central nervous system for a modern building.
That's a great analogy.
And the equipment used in a BAS, does it mirror PLC hardware?
It mirrors the concepts, but the philosophy is a bit different, reflecting that integration and decentralization goal. You do have central controllers, sometimes called supervisory controllers, which act like the main processors, managing overall communication, data logging, and providing the main user interface. However, a key difference is the heavy reliance on field equipment controllers, or FECs. These are smaller, specialized controllers, located physically close to the equipment they manage, like an air handling unit controller in the mechanical room or a zone controller above the ceiling managing VAV boxes.
So distributed intelligence.
Exactly. These FECs often perform their local control loops autonomously. They talk back to the central controller, but if that central communication link fails temporarily, the local FEC can usually continue controlling its equipment based on its last known set points or a default strategy. This distributed architecture drastically reduces wiring compared to running everything back to one central PLC, and it significantly improves reliability. You also see various distributed I/O devices, sometimes resembling those brick PLCs we talked about, connected to the FECs. And of course, various user interfaces, dedicated HMIs, specialized software running on PCs, web interfaces, even mobile apps for facility managers.
That decentralized control makes a lot of sense for a sprawling building system. Our sources mentioned a specific critical example, the smoke control system integration.
Yes, that's a vital function often integrated within the BAS, working closely with the fire alarm system. When a fire is detected, the smoke control sequence activates. Its job is complex. Manage smoke spread using fans and dampers, potentially pressurize escape routes or stairwells to keep them clear, exhaust smoke from the fire zone, but do all this carefully to avoid inadvertently fanning the flames by supplying too much fresh air.
And these systems need special interfaces.
They often have dedicated firefighters' smoke control panels, FSCPs, simplified interfaces, allowing firefighters to manually override or command specific fans and dampers during an incident. The required operation can even vary depending on the building type. For instance, smoke control in a hospital where occupants might not be easily evacuated can have different strategies than in an office building. It's highly specialized and life critical.
Beyond safety, a huge driver for BAS is efficiency, right? Energy savings.
Absolutely. That's often a primary justification for installing a BAS. It constantly monitors environmental conditions, temperature, humidity, CO2 levels, maybe even outdoor air conditions. Based on this data, plus program schedules and occupancy information from sensors or access control logs, it intelligently regulates the HVAC systems. It avoids overcooling or overheating, utilizes free cooling when outdoor air is suitable, and minimizes energy use during unoccupied periods. Similarly, lighting is controlled precisely dimmed or turned off when spaces are empty or when there's sufficient daylight. All these coordinated actions can lead to significant energy savings and operational cost reductions.
And for all these different controllers and devices from potentially different manufacturers to talk to each other, there needs to be a common language.
There does. And the dominant standard protocol in the building automation world is BASnet, which stands for Building Automation and Control Networks. It's an open standard designed specifically for this purpose, allowing devices from various vendors to interoperate seamlessly within the BAS network.
Wow, okay, we have definitely covered a lot of ground today. From those fundamental, tough-as-nails PLCs quietly running the show in factories, all the way up to these sprawling, integrated building automation systems that manage the incredibly complex dance of an entire intelligent building. It really is a hidden world of amazing complexity and clever engineering.
It really is. And, thinking about the sheer scale of automation we've touched on, from just a simple button press triggering a very precise, immediate mechanical action, all the way to a sophisticated BAS making subtle, building-wide adjustments based on predictive algorithms. It does raise an interesting question, doesn't it? How does understanding these foundational brains, the PLCs and the BAS controllers, how does that maybe shift your perspective when you walk through a modern airport or hospital or even just your office building, all those smart environments you interact with daily? And maybe what's the next frontier for these systems? As they get even more interconnected, maybe with AI, what new capabilities might emerge?
That is a powerful thought to leave everyone with. We certainly hope you enjoyed this deep dive into the really fascinating world of PLCs and building automation systems. Until next time, keep digging, keep learning, and keep asking, how does it all work?